Okay, our session is being recorded. Make sure you're on mute when you come in the classroom. Let's see, I need to maybe, if I can mute people from here, yeah, I think so. Okay. All right, we're in good shape. All right, we're starting week 2 of our mini piece in the middle of the course called End User Analytics Tools. This is where we do a brief look, and it is pretty brief, at developing some models. Now, of course, the heavy lifting for model building comes in the Data610 course, where we get into SAS Enterprise Miner, some larger data sets, et cetera, and we explain in great detail what's behind building the models. But it's still good to have some practice building the models. I know you probably did a little bit of that in 600 with Rapid Miner, and of course you're doing a little bit here with prediction and with Big ML. So you'll have the opportunity to try a few things, learn a little bit about models. Now, one of the things about models that's very important, there's a lot of things that are important, but a lot of things that's important is to figure out how to evaluate the models. As I've said several times already, the heavy lifting, the computational burden that was there just a few years ago is gone. With any of the software tools you use now, you hit the enter key and the models are built. So what it does is place a premium now on doing things differently. You have to understand the model. You have to frame the problem. You have to, as I said, interpret and explain the model. You have to sell the answer. You also are probably going to build multiple models, not just one. In the old days, when it was tedious to build one, people would spend a lot of time, experts, trying to glean insights from the data set before they built the model, because it's going to take so long to build the model because of the computational burden that they had to do it right the first time, or do it as well as they could the first time. Now, I think the approach is entirely different. I would recommend build multiple models, many, different types, different techniques, different tools, and then have a way of comparing the models for which one is the best, and a combination of best means accurate and easy to explain. So sometimes a model that's best would be a model that may not be quite as accurate, but a little bit easier to explain. For example, decision trees are, as you'll see when we finish, by the time we finish this course, a little bit easier to explain, a lot easier to explain than something like a neural network. So we'll get to that. So tonight we're going to take a little bit of a look at a couple of key things, and you'll see that when we get to it. We're going to look at analytical tools and discuss accuracy charts especially, and then we'll talk about what's week 7. Okay, so where do you start? You're going to build a model. Where do you start? Well, there's a couple of key decision points that I see, and we're going to go through these. What kind of data do you have, and what kind of decision do you have to make? Second decision point, which technique is appropriate? And, of course, realizing that several techniques exist, you may want to use multiple techniques. And then that's the technique. Now, within each technique, like classification or prediction, there are models, neural nets, regression, decision trees, and others. And of course, as I said, not just based on accuracy, but can you sell your results? So let's go through this a little bit at a time. I've mentioned this very briefly, but let me review it a little bit. We really have 2 mega kinds of models we can build. We can build a supervised model. We can build an unsupervised model. The difference, of course, is that the supervised model, you have to be able to identify inputs, or at least potential inputs. In other words, the variables that you think are related to the answer, and you have to have a target variable. What is it you're trying to predict? Is it likelihood of a person churning or leaving the company? Is it likelihood of a fraudulent transaction? Is it whether a person will pay back a loan or not? What is it you're trying to predict? But for a supervised model, you're going to have a target as well as input possible predictor variables. With an unsupervised, you still have a lot of input variables, but you don't have any target. There's value in both kinds of models. So for the supervised, again, we have past data cases where we know how it turned out. We have a bunch of inputs that are potentially related to the output, at least correlated, maybe not causative. And we try to figure out, excuse me, we try to build a model, and that's where the computer comes in handy, of course. In building the black box in between, how are these inputs related to the output? Now, the computer is basically, we call this machine learning because it's learning. Now it's learning very crude way. In some cases, it's trial and error. In other cases, it's using some quantitative techniques, such as we apply in regression, forward selection, backward selection. In the case of decision trees, it's using an index to figure out how to split the data. We don't have to worry too much about that in this course. But basically, the learning relationship figures out a mathematical relationship between inputs and the target, the output of interest. Now, once it's learned that relationship, it says, oh, I see, when you have X, Y, and Z in certain phases, when certain values for those three variables, the answer is 80% likelihood of churn. When you have X, Y, Z with different values, the answer is 10% chance of churn. So what do I do with that? Well, then, of course, we take new cases. We look at our customers we now have, because remember, this is past data. We look at our customers we now have, and we run the model through there, and we say, oh, my goodness, look at these customers. They have a high likelihood of churning, meaning leaving the company. These other customers, very low likelihood. So what are we going to do about that? Well, then we might take some action, give the ones who are likely to churn some kind of a discount or an early renewal or who knows what. We'll talk about that later. Remember, you don't have to predict the new cases perfectly. You just have to be able to do it better than anything you're using right now. Now, there's also a step in between. Once the algorithm learns the relationship using this past data, we train it on a set of cases called the training set, but we also reserve a small set, maybe 20, 25% of the past data cases. We don't show those to the model as it's learning. Once it thinks it's learned all it can and thinks it has a pretty good model, then we say, all right, here's your midterm exam. Let me show you these other cases. I know the answers, but I'm going to show them to you and let you guess at the answers, and then I'm going to evaluate how well you did. So that's called the test set. And it's very important to have both sets always, because the training set is where it sees over and over and over and figures out the relationship. The test set is the midterm exam to see whether that relationship holds for new cases. And then if it holds for new cases, we can use it on cases where we don't have the answers. So it's a neat stepwise procedure. We'll talk more about that. Now, with an unsupervised approach, where you do not have a target that you're trying to predict or identified, you still have past data cases, but you do not have an output of interest or a target. So why do I want to do this at all? What's the value? Well, there are still algorithms, clustering and association, that will allow you to learn something, and that something can be very interesting and or significant about your data set. For example, clustering models help group things, high, medium, low. Maybe these are customers that tend to buy a lot. These are customers that tend to buy a modest amount. These are customers that don't buy much at all. Okay? So we can cluster things, and we might want to market or segment. That's called segmentation quite often instead of clustering. Segment the market or segment our data into like items, and we know something about those like items because we can look at the variables that cause them to be in those certain clusters. Very insightful, very useful. I don't want to make it sound like it's not of value, because it's very valuable. And the other model we use is association, where we try to say, if you bought X, you're likely to be interested in purchasing Y. So I'll say a little bit more about that. So we have supervised and unsupervised. And the first decision you'll have to make before you build a model is to decide which kind of a model you're going to build. And if you have a target variable that you're trying to predict, whether it's continuous or discrete, whether it's categorical or a number, you will have a supervised model. If you just have a data set full of stuff and you want to learn something very interesting, very insightful, and perhaps very useful, then you would build an unsupervised model. Okay, so the second decision point is what I call, okay, what technique do I want to use? And there are several out there, of course. Classification is used, classification techniques, and we're going to get into the specifics under that in a minute, but the second point is, okay, do I want a classification model, a prediction model, or a time series model? Let's say we're dealing with supervised, because that's where those would come in handy, because you have to have a target to use these three approaches. If you're trying to put something into a category, your target is a category, high, medium, low, will pay back, won't pay back, pay back on time, pay back late, pay back never, and so forth. Then you have a classification model. It doesn't have to be binary, by the way. It doesn't be binary. It can be something like good, bad, in between, fraudulent, not fraudulent, bankrupt or not. You know, I'm predicting whether a person will go bankrupt or not, will pay a loan back or not, going to commit fraud or not, leave the company or not. Again, does not have to be binary. It's just that to be a discrete number of categories that the target variable falls into. That's called a classification type problem. If instead you're trying to predict a continuous variable, like a number on a scale, or a continuous scale, then it's called a prediction problem or an estimating problem. So maybe you're trying to predict the likelihood someone will do something. Well, now put them in a category, you're predicting a number to go with that. Or you're trying to predict the amount that they will earn over a lifetime or something, okay? If you're trying to predict a continuous variable, if that's your target variable, you have a prediction, or sometimes called estimating problem. And the third series, or the third kind of technique we use for supervised models, is time series. And here the data are aligned over time. Yesterday the market was 13,000. Yesterday, the day before, it was 12,950. The day before, it was 13,902. I'm trying to predict the market for tomorrow. Sales last year, the year before, or last month, the month before were XYZ. I'm trying to predict what sales will be next month. We call that time series forecasting, okay? Again, so we have three kinds of different techniques, if you want to call them that. So the third decision point, once you've decided, yeah, I'm going to do, I have a supervised data set, and I'm going to do one of these kinds of models or techniques. I'm going to use one of these kinds of techniques. The third point would be, what specific model do I use? Now, under classification, under each of those, we have several choices. Under classification, we have these. At least these are the ones in the software that you're using called prediction. The main ones that are used often in the world are decision tree, logistic regression, and neural network. So decision tree, logistic regression, which is a form of regression designed for classification problems, or problems where we have categories as the output, and neural networks. Those are the main three. We also have a couple of them. Naive Bayes, which is basically a baseline, says do whatever the average is, and classification rules, which are very similar to decision tree, slightly different. You will also notice in prediction that there are two sets of each algorithm for the most part. One set is the Microsoft algorithms that come with product. The other set are the R, and you're familiar a little bit with the R programming language, the open source language, the R algorithms. Companies have slightly different ways of implementing the same algorithms. So all classification models don't work the same. All estimation models don't work exactly the same. And again, my solution or my suggestion would be, why not try all of them? It only takes a click and you got them. And then you have to be able to sort them out. And we'll talk about that in a minute. So these are the main ones. Now, again, the big three are decision tree, logistic regression, neural network. Logistic regression and neural network are much harder to explain than decision trees. They have more stringent data requirements than decision trees. They don't deal well with skewed distributions. They don't deal well with missing values. Decision trees don't have a problem. So you might be thinking, well, why don't I just use decision trees all the time? And the answer is that oftentimes logistic regression and neural network models are more accurate. So if it's close, then maybe a decision tree would be the way to go because it's easier to explain. If there's a big difference in the accuracy, then you may have to go with something more complex. Or not really more, it's more complex in some sense. It's actually basically different. Okay? Now, when you're doing prediction, which means you have a continuous target variable, a number that's continuous, 2.1, 2.6, 2.8, 4.6, whatever the scale is, you still use a lot of different kinds of models. The main ones here, however, are linear regression, which is the equivalent of logistic regression, but something that we use for continuous variables, and very well known, very popular technique. We can also use neural networks and regression trees. Now you see logistic regression mentioned here. It can be used. The main ones you'd want to use for a prediction column are linear regression, neural network, regression trees, which are just a form of decision trees to handle continuous outputs, the main trees. We also have these others, Gaussian trees. Everybody has their own little tweaks and spin-offs. I'm mentioning the ones that mainly use. You can use them all, or you can just stick with the main ones because they're likely to be the better ones when you do it, likely. If it were easy to say which model would do best or which technique would do best, then we'd have a very simple guideline for you to use. The answer is, unfortunately, that's not true. It's not even easy to generalize which models work best for which kinds of data sets, except that we can give you some general rules and do that in 640. Okay. All right, what techniques can we use for unsupervised where we do not have a target variable? Well, I mentioned the two we have, two main ones. Cluster analysis, which will separate the data set into clusters, homogeneous, fairly homogeneous clusters. It'll say, well, this one's more like that than it is the third one, so I'll put it together. And it keeps doing that over and over again. And you can decide the number of clusters you'd like to have, or you can let the algorithm figure it out. And it's very insightful sometimes to get groupings. When you get to big ML, which is downstream, you'll see they have a great clustering algorithm. And they have a great example of how to use it. But you can certainly do some same kind of clustering with prediction. And then the other tool we use for unsupervised is this market basket analysis, which people like Amazon and all use. They say, well, Steve's looking at drivers, golf club drivers, so let's show him a couple of putters. Or he's looking at a book about virtual reality, let's show him a book about something related to virtual reality. And of course, the idea would be that those models are built on knowing, and it's not just as simple as the title or the content. It's much more sophisticated. You can get association rules that are very complex. Let's say, they look at the relationship between many purchases or many views of things or many customers who bought X and other things and try to figure out the likelihood of customers who bought X buying product Y. And if that likelihood is high enough, it might be beneficial to you to advertise that product or display that product or whatever. So this is all sort of things you have to think about when you take your data set and say, all right, I'm ready to go build a model. Okay? Now, it's not complicated, in my opinion, because the fact that, again, instead of the old way where you had to decide on one technique and do it one time and do the calculations either by hand or with a calculator or a spreadsheet, you get to build a lot of models very quickly. And then you have to have what? Some way of sorting them out. Now, when you're developing the models, let's say you have a model that has 15 input variables and, of course, a target. The tendency for people who are just starting to build models is, well, geez, I'm just going to throw them all in there. Why not just dump all the variables in and see what happens? Well, you run into problems. First of all, it's a lot more data to collect. That's the simplest thing, of course. If you have 15 variables and you want to use them all, then you better collect 15 variables for every possible case that you're going to use. That's not the biggest problem. The biggest problem is when you get variables and dump them all in, you may have variables included that are correlated with each other. And that's going to throw off the model, okay? They're not independent. We want independent variables. We want only variables that are relevant to the problem. We don't want to predict the stock market by using shoe size. Even if you find a good correlation, no one's going to believe it. It's probably spurious. I mean, you can correlate the number of matches a person strikes in a day with their likelihood of getting lung cancer, but they're not related. They're striking the matches to light cigarettes, which may or likely are related, okay? So the first thing you'd want to do, even if you're going to use, you're going to use an automated tool to build the models, but the first thing you want to do is make sure you're picking wisely from the possible set of input variables. You don't want to just dump them all in there. As I said, you want variables that are highly relevant, and certainly you want variables that are independent. The other interesting thing is sometimes a subset, not just sometimes, but quite often, a subset of the variables works better to build a model than the complete set. Interesting, right? A subset. The other confusing thing, or adding complexity to the problem, is sometimes when you do the variables you think are most highly related to the output variable, the target variable, at least based on your first indication, it turns out a set of the poorly related variables independently, when put together, form a nice relationship. If you remember when I showed you prediction insight now, rather than the analytics piece, where you did that first thing, it came up with that screenshot that said, I have looked at the basically that says, I've looked at variables one at a time and found how strongly they are as influencers. Remember the influencers chart. I have looked at them one at a time. I've not looked at combinations. So it might be that you find a better combination using some of the variables that don't show a strong correlation when looked at one at a time. Isn't this fun? This makes it so much more fun. And actually, this is good news. If it were too easy to build models, then you wouldn't be able to make a great living as a data scientist. If it were too easy to explain the models, to frame the models, to sell the models, to implement the models, you couldn't make a good living as a data scientist. It is getting easier and different, although there's still a strong value for having someone who understands the models, knows about the kinds of things such as picking the right features, checking the right accuracy measures, building the right models at the right time, interpreting the answers. So that's really where the focus is. You still need to know something about the mathematics going on behind the scenes. We cover that in great depth, as I said, in Data 640. Not in this course, not too much in this course. Degrees of freedom. You know, what models want, of course, is for all the variables that you're going to include, lots of cases that take on lots of different values in different combinations. That gives the model a rich, robust environment from which to learn what the real relationship is between the inputs and the answer. So the more variables you decide to include, more cases or instances you're going to have, and the more varied the values in those instances need to be in different combinations. Okay? You know, when I built a neural network model 25 years ago, when neural nets were just very difficult to do, I built a very small one with, I had a class and I was trying to predict their weight based on their height and waist. So 2 inputs, 1 output. I collected the information from the students. I collected their height and their waist, and I used those as inputs, and I built a neural network to predict their weight. It didn't do very well. So what I said was, oh, you know, there's different body frames. There's short people, there's tall people, so height and waist may not be all I need. I may need to know gender. Well, if I add gender in, now I need short, thin women, short, heavy-set females, medium-sized females of both types. I need men of short, heavy-set, short, thin, men of both types, male variables of both types. So the more variables you add, the more cases you need. So I had to collect more data. And it ended up doing a lot better the more data I collected, but that meant more cases, it meant more values, it meant instead of using a class of maybe 50 students that I had, I needed to collect data for hundreds of students. So again, the more features you have, the more complex the model can get, the more convoluted it can get if those features are interrelated and not independent. And so this becomes, I wouldn't say it's a guessing game, but a little bit trial and error, a little bit of science behind it. But you want to look for feature, what we call feature parsimony. Use only the key features. I'll give you an aside that sort of turns a little bit of this on its ear, and that is decision trees have a great way of selecting the most salient features. Regression models have a reasonable way of selecting the most salient features. Neural networks have no way of selecting the most salient features. So you sort of have to help them. Whereas decision trees basically can do a pretty good job on their own most of the time. It doesn't mean it might not pay to go back and try picking them yourself, but decision trees have an algorithm that basically looks at all the possible selectors, features, and picks the best ones in the descending order. Again, we won't do much on explaining all of that in this course. So what are the criteria? How am I going to pick the features to use? Well, obviously availability. It doesn't do much good to say, I can tell you I've got a great model that predicts the market closing. All I need to know is where the market was at 1 nanosecond before it closed. Well, yeah, but that's not going to help me much. Again, I've mentioned the story of Netflix, which said anyone who can build a model that gives us a 10% improvement on recommending movies to people and can show that will get $1 million. And after a fairly lengthy period of time, months and months, this was one of the competitions out on Kaggle where people put competitions like this with rewards. A group did build a model that actually was proven by Netflix to improve their movie recommendation by more than 10%. They gave them the $1 million. However, they never implemented the model. It was too complex, took too long to run, too complicated. You know, you're not going to sit there on your website for a extended period of time waiting for a movie recommendation. Even if it is a better fit, it just was too cumbersome. So you have to look for features that are available, that can be retained, that are timely, that are accurate. You also have to remember that we're using past data, building a model that we're going to use to predict future or current cases. So it has to be something that's fairly stable. You know, if you're in a very dynamic business where the past data means meaningless to predict the future, this isn't going to work at all. So it has to be salient, it has to be independent, it has to be inexpensive. It doesn't do any good to spend $10 to collect a variable that's going to save you $6. And of course, volatility, stationary. You don't want variables that flop all over the place. So these are some very good hints, if you will, suggestions, if you will, about how you might want to go about selecting your features. So what do you have to do now? You have to select your model based on your data type, based on whether it's classification or numerical, based on whether it's supervised or unsupervised. You have to think about which features to use, especially if you're building a neural network or a regression model. Now what do you have to do? Well, after you build the models, you have to be able to evaluate the accuracy. So one more slide here on model development. Some suggestions, again, out of this very good book or article talking, well, it's a book, talking about the 7 sins. Consider using cluster analysis to see if there are feature sets that separate into clusters. You know, if you say, forget the target variable, I've got a target, but I'm going to exclude it from the model and just pretend I don't have it and build a cluster model, you might get some insights into how those clusters are formed that lead you to think those are the key variables. If the clusters are formed based on a certain chemical ingredient, for example, in wines, you know, all the wines that have a lot of sodium go here, all the wines that have a medium amount of sodium tend to be in this cluster, all the wines that have low sodium are in a third cluster. If that's what comes out of your cluster analysis, then you might tend to think, well, maybe sodium content is a key way to predict what kind of wine I have. Now, this was certainly much more important. Again, you can see this is from a 2001 book. I've always used this book, but this was much more important when you were only building one or a small number of models. When you're building multiple models, I still think it might be better just to keep trying various things. Something else you want to do. Oh, yeah. One of the things cluster would do is help you identify outliers. You know, suppose you end up with 4 clusters and 3 of them have 33% of the data sets in each of them, and the 4th cluster has only 1 data point. And why? Why would that 4th cluster have just maybe 1% or 1 data point? Because they're such odd cases that they don't fit in any of the other 3 clusters. Everything else fits nicely into one of those 3. This other small percentage, it's so weird that I have to put it in a separate cluster or clusters. Well, those might be outliers. Those cases might be outliers. You may want to exclude them entirely from your data set analysis. You know, when you start to eliminate outliers, we talked a little bit about that. It's a tricky business. Sometimes outliers are legitimate points. Sometimes they're typos. Sometimes they're missing cases, and so the default is to put in 999 for age. So it says whenever the age is missing, put in 999. Well, that means the person was very old, which of course is not true. Or put in 0. Well, if the person's age really 0. So cluster analysis can help detect outliers. You might want to think about balancing the case outcomes. I'm going to say a little bit more about this. This is called the 99 versus 1 problem. If you have a terribly imbalanced data set, let's say you have 10,000 cases, 9,900 of them are people who paid back a loan, 100 of them are people who did not. Well, you turn that over to a classification model, it's going to say, oh, piece of cake. It will predict that everyone will pay the loan back. How accurate will it be? 99%, because 99% of the people do pay the loan back. And that's because when it looked at the training set, it said, oh my God, just about everybody pays the loan back. This is easy. I'm just going to predict everybody pays it back. That's really not what you were looking for when you built the model, was it? You were looking to identify the people likely to not pay the loan back. So even though the model is good at predicting a large number will pay it back, in fact, it's going to predict everybody pays it back and be 99% accurate, it's of no value because it doesn't help you identify the people likely to not pay the loan back. So what would be better? It would be much better if you had a data set where 5,000 of the cases were people who paid the loan back, 5,000 of the cases were people who did not pay the loan back, because now it's a 50-50 coin flip. And so the model says, oh my goodness, I got to look a lot harder at figuring out what relationships among and between the variables really tend to say people will pay the loan back or not. Now, it may get from that 50-50 case to 80% able to predict who won't pay the loan back, which would be great, or 70%. Still be better than 50-50. So there are ways of balancing the model set. We'll talk a little bit about those. And those ways of doing it are decimation. Now, decimation is pretty tough. It says take out, let's say we're back to the 9,900 that did pay it back and the 100 who didn't. Decimation says take out 9,800 of the ones that paid it back and keep 100 of them that did pay it back and 100 that didn't. Well, yeah, you balance the data set, but you got rid of 98% of your data. So that's not really usually a good way to go. Replication says, I'm going to take these 100 who didn't pay it back, and I'm going to keep the 9,900 who did. I'm going to take the 100 who didn't pay it back, and I'm going to replicate or duplicate those cases over and over and over and over and put them back in the data set. So now I'm going to end up with 9,900 that did pay it back and 9,900 that didn't, although the 9,900 that didn't are really the 100 duplicated many times. Sometimes that works. Then there's weighting. Some software will allow you to put a heavier weight on the cases that are rare, and that's another approach. A lot of ways to do this. You want to avoid duplicative cases. You don't want to have a variable that's yearly income and monthly income. They're basically the same thing, except one's divided by 12 or one's multiplied by 12, depending on how you view it. So you want to get rid of those. You want to handle temporal data that changes over time, carefully. When I used to teach a course in neural nets, I had students who wanted to predict the market, always want to predict the market. Well, if you use data from the the late 80s when the market was booming, and use only that data to predict the future, well, the model's never seen a down market, so it predicts always up markets. So you have to be careful with temporal data. And then, of course, I said before, you always have to have a test set and a training set, always. Training set to train on, test set midterm. Okay, so when we talk about the midterm exam, we want to transition now into, okay, how do you grade the midterm exam? How do we decide whether you pass, you being the model? We give it the training set and say, train. We give it the test set one time and say, all right, what'd you get on the test set? Because I know the answers. I'm not telling you. You tell me your guesses at the answers. And since I have the answer sheet, I can figure out whether you were able to predict correctly or not. Well, we have multiple ways of determining the accuracy. especially for classification models, which are actually more prevalent than prediction models. Excuse me. We have many more classification models than we do prediction models. Remember, prediction is for a continuous variable. Classification is for when you're putting it into a category, classifying it. So we're going to go through these outcome assessment tools briefly. Again, they're used in multiple ways for multiple purposes. Now, it's a little bit easier, and I'm going to start by talking about the measures we use for prediction models. Remember, here you're predicting a continuous variable. So we're basically measuring the prediction versus how much you missed it by, aren't we? So it's the error term. We're basically trying to get a handle on the error term. Now, the easiest way to illustrate this is with this little drawing at the bottom. Now, this is only for 2 dimensions. Almost always, we're building models that are n-dimensional, but we can't really draw pictures of n dimensions, but the concept is the same. If you have a 2-dimensional model, let's say it's a linear regression model, which is what this illustrates, but if it's true about any numerical model, prediction model, we have a linear regression model. A linear regression model means it's going to be a line in 2 dimensions, a plane in 3 dimensions, and who knows, a hyperspace, a hypervector in multiple dimensions. But anyway, here's our prediction, the line, and here's what really happened. So every one of these dots that's not on the line has an error term, the distance by which it missed being on the line. The line says, I think it should be here. Based on the input and the prediction, I think it should be on the line. So these are all errors. All the vertical distances up and down from the line for each of these little dots is an error. Here we have no error, do we? If you have no error, you're going to get an R squared, a coefficient of determination of 0, meaning a perfect fit. Okay, it can either be upward sloping or downward sloping, but it's going to be a perfect fit. Okay, and R squared is basically a measure of how much of the variation in the input, or how much of a variation in the target is captured by the inputs. In other words, how good a job did you do of picking the right input variables? And how well do they capture the variation? Well, if our input variable captures all of the variation, that's a perfect predictor. If it captures a lot of the variation, you'll get an R squared, maybe 0.5, maybe 0.7. Those are still very good. If it captures none of the variation, you get an R squared of 0. Okay. We also use something called root mean squared error. And we use other terms I should have on the chart. Average error. Basically, we take these errors, okay, and we get the average. That's one term. We can get the average squared error. We take the errors, and to get rid of the signs, we square them and get the average. Add up all the errors, divide by the number of points, number of cases. That's the average squared error. We can also get the root mean squared error. How do we do that? Take all the errors, square them, so we get rid of the signs. Some of them are negative, some are positive, but we square them to get rid of the sign. We add them up and get the average. That's the mean squared error that I just mentioned. And then we take the square root of that. Why take the square root of that? Well, because we squared them in the first place, so if we want to get the dimensionality back to something that's similar to what we started with, take the square root. You'll see these all used. They have different meanings, but those are the meanings. You can look up in very much more detail if you'd like about these error terms. So the root mean square error is one that I like because, again, you get the dimensionality back. It says, oh, okay, you're basically saying what is the average error you missed it by in terms that make sense. So add up the errors and square the errors, add them up and take the average, and then take the square root to get back to something meaningful in terms of units. So these are accuracy measures, fairly straightforward, and basically right from statistics that we use when we have prediction or continuous numerical problems or models. Now, when we use classification models, some of these measures of accuracy might be new to you, but they're good ones and they're very useful. And each of them has its own use. Excuse me. So rather than focusing strictly on an error term, we don't have that because we're predicting an outcome. We're saying, yes, they're likely to turn. No, they're not likely to turn. We're predicting a category, so we don't have the same kind of numerical measurements to use the same kind of statistical tools on. So what do we use? Well, we use several things. First is a confusion matrix, sometimes called a classification matrix. It takes the actual, remember we use this against, well, you could use this against the training set. It's going to do very well. But the real test is to use it against the test set and see how well it does. You'd probably want to do it against both. If it's 82% accurate on the training set and 80.5% accurate on the test set, that's pretty good. Won't do as well on the test set as the training set. If it's 82% accurate on the training set and 50% accurate on the test set, you got a problem, because that means you probably overfit. We'll talk about that some other time. Overfit the training set. And you can't overfit models. You can do so well on the training set, but not generalize at all. Okay. So we have past data, right? And so we know what actually happened. Let's just say this is a yes or no outcome. Classification model where there's only two outcomes, yes and no. So this is what actually happened, and this is what's predicted to happen. So when it actually was a yes and the model predicted a yes, that goes in square A, and those are called true positives. And that's a correct thing, isn't it? The model said, yep, yep, yep. And then in the actual class, we look at our cheat sheet for the midterm. We say, yep, yep, you're getting those right. When it actually was a yes, but the model predicted no, that is what we call a false negative. The model says, no, this person did not leave the company. We say, well, they did. You got it wrong. So you said no, negative, and it turns out they did leave. So that's a false negative. Same thing for the no's. We got some customers who did not leave the firm, let's say, and the model predicts they did not leave. That's square D. That's correct. True negatives. And if they did not leave the firm, but the model predicted they would, those are false positives. Now I'm using the churn model. This is just as useful for medical problems. Trying to predict whether someone has cancer or something like that. You've all heard the terms false positive, false negatives, type A, type 1, type 2 errors, and that's basically what this is. Now let's take it a little further. And let's put some, again, true positives, true negatives. So the ones in black are correct. The model got those correct. The ones in red, the model got those wrong. So what do we do with that? So there's going to be numbers in here when you run it against actual test cases, of course. There's going to be several metrics. One is the overall accuracy of the model. What's the overall accuracy? Well, the total it got right, A and D, divided by the total. So the true positives plus the true negatives divided by the total number of cases. If it were a perfect model, this number and the bottom, the denominator and the numerator would be the same number, wouldn't they? Because there wouldn't be any false negatives or false positives. That's not going to happen. Remember, your ultimate measure is always, are you doing better than we can do without the model? It's never, are we perfect? Because you're going to lose that argument. Okay. Again, we have some other measures. So that's overall accuracy. But we have other measures. We have something called sensitivity. Sensitivity is how well it does on predicting yeses. So it's the true positives, which it predicted to be yes, over the total positives, which is A and B, right? So we call that sensitivity. How sensitive is it? How well does it do finding the yeses, the outcomes that are positive? We have something else called specificity. Basically, how well does it do on the nose? How well did it do on the nose? Well, down here were the nose it predicted. So D over D plus C, because these are also nose. And we call that specificity. So again, those are terms you'll have to get used to. Sensitivity, how well it does on the yeses or the positives. Specificity, sensitivity, how well it does on the positives. Specificity, how well it does on the negatives. And that's for a binary outcome. Now, I'm going to do a little example just to show you this. This is the 99-1 problem. I've already explained that, so I think I can skip over this. Again, if you had 9,990 zeros and 10 ones, the model will predict everything to be a zero because it's 99.9% correct. That's not what you want. For a classification model, you'd like to have roughly an equal number. So let's put go back to the confusion matrix with some costs to show you why overall accuracy might not be the thing of interest. You might be much more interested in specificity or sensitivity. Just like a doctor might be more interested in not having a lot of false negatives. In other words, sending people home thinking they're okay who aren't. And also might be more interested in not having a lot of false positives, telling people they've got to get more tests and this and that, when it turns out they really didn't have a problem. By the way, you say, well, I'd like to get rid of both. You can't get rid of both. There are trade-offs. You can lower one, but you can't lower both because it comes at the expense of one. You'll see when you do the calculations, you can't do that. This is a business example. Let's say we have some costs involved, and I'll show you a little example here right out of a book that I think is very illustrative of why specificity and sensitivity often come into play. Here's our same confusion matrix, only this time I'm adding some costs to go with it. Okay, there's a cost of, if you predict a yes and it is a yes, it has a certain cost. If you predict a no, but it was a yes, there's a different cost. If you predict a yes and it was a no, there's a different cost. If you predict a no, there's a no, and it is a no, there's a different cost. And here are the costs figured in. Now this illustration, these are cost figures. I'm emphasizing that because that means what? Lower is better. Lower is better. Okay? So I didn't make these up. They came right out of this example, so I'm just going to put them right in here. So again, if it's actually a positive and you predict a positive, your cost is -1, which is good. That means you made a profit. If it's actually a positive, but you predicted a negative, your cost is 100. That's really bad. Really bad. So if you predicted a no, but it was actually a yes, that's going to cost you big bucks. If you predict a no or a minus, and it actually is a plus, that's going to cost you, but only 1 unit, $1. And if you predicted a minus, and it really is a minus, this is a predicted minus, and this is the really is minus, that doesn't cost you anything. It's a push. Okay, so let's say I run 2 different models using 2 different sets of inputs. Maybe even they're 2 different kinds of models. One's a decision tree, one's a regression model. It doesn't really matter. But I have 2 models to compare, model M1 and model M2. And here's how it came out when I ran each of the models against the same test set. Okay, model 1 got 150 true positives. It also got 40 false positives. Got 60 false negatives and 250 true negatives. So again, the black numbers are correct. The red numbers are wrong. Model 2, 250 correct positives. 45, it predicted negative when they really were positive. Remember, this is the actual, the rows. And same thing, 200, great, doing great on predicting the negatives. Only 5 did it predict positive that were negative. So if we compute the overall accuracy, remember the accuracy is the number we got right. So 150 plus 250 divided by the total. So that's 400 divided by 500. So our accuracy here is 80%. Right? Got 80% right. We predicted 400 out of the 500 cases correctly. What's the accuracy of this one? Well, we predicted 450 out of the 500 cases correct, so it's got a 90% accuracy. If you stop there, excuse me, if you stop there and said which model's best, you'd say, well, this one's more accurate. But we had cost figures, didn't we? So let's see what this one's going to cost us. Remember, this 150 gets multiplied by -1, so that's good. 150 times -1. But this 40 gets multiplied by 100. That's bad. This 60 gets multiplied by 1. That's also slightly bad. And this 250 gets multiplied by 0 for a total cost of $3,910. Remember, it's cost, so lower is better. If we go over here and say, well, the 250 here, that's really good. We made $1 on each of those. The 45, we lost $100 on each of those. The 5, we lost $1 on each of those, and the 200 didn't cost anything. Turns out the cost is higher. Even though it had fewer, it had more correct answers, the fact that it had a significant number of false negatives They thought these were negative when they're actually positive, and those were opportunities foregone that cost us big bucks, meant the cost of this model was greater than this one. So when you have a business problem, you have to look at the cost figures and fold those into the confusion matrix, not just look at the accuracy figures. And I think, I'm working much harder now to try to give you, I would like to see more data sets that had some business numbers associated. Because the bottom line is, yeah, it's nice to build models and look at the overall accuracy, but the bottom line is, of course, you're going to have to apply this somewhere in the real world, and you're going to have to likely have some cost figures. Or you're going to have to apply it in maybe a medical situation, and you're going to have some imputed costs of predicting something wrong. Sending someone home who has a problem and missing it, or doing a lot of tests on someone who doesn't have a problem because you thought they did. Something to think about. Now, that's the confusion matrix, which I like. There's something else I like a lot called the ROC curve. Okay? The ROC curve developed in the 1950s for signal detection to noise. Very interesting origination of this. But basically, it's going to plot the true positives against the false positives. So it's going to look at the fact that it got certain ones right and certain ones wrong. And you'll see how this works. Now, let me show you the curve. Here it is. This is one ROC curve for one model. This is kind of the ineffective test, just kind of a 50-50, separating the solution space or the total class space into 50% and 50%. So what you want to do is plot your ROC curve. Now, I'll talk about how you get this ROC curve in a minute. And what you'd really want to do, the real value of an ROC curve is certainly to have it and look at it, but to plot multiple ROC curves. You'd like to see all the models, put all their ROC curves on this, and then you can be able to tell which model is best without cost figures, but from an ROC curve point of view, because the more space it takes up, the better it is. An ideal ROC curve would be where? Well, remember, this is the false positive rate, and it's 1 minus the specificity. So you want to be over here. This is the sensitivity rate, and you want to be up here. So the ideal place is right, I can't point at it, but it's right up here in the top left, right here. A perfect curve would go straight up and across, and it would encompass 100% of the area under the curve. You may see that term used, AUC, area under curve. It's a way of measuring how good a model you have. You get something 0.8, 0.9, that's considered a great model. 0.5, 0.6, an average model. Below 0.5 or 0.4, pretty weak model. Area under the curve. How much of this total rectangle is under my ROC curve? So this is one ROC curve. You really want to plot, if you build multiple models, you put them all on there. Of course, the software does that for you. So where does the ROC curve come from? Well, look at all these points on here. Here's a point, 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 here's a point. Those are not points plotted on this axis. Those points come from changing the threshold of the algorithm. All right, here's where we have to do a little sidebar. When we're doing a classification model, let's stick with just two outcomes, a yes and a no, okay? 0 and 1, up, down, whatever you want to call it, but yes and no. When we're doing a classification model, what comes out of the model is a yes or a no. But behind the scenes, of course, there's math. There's math calculations. And so every case that goes through the model gets a calculation behind the scenes. If that number comes out 0.5 or higher, the model says this is a yes. If it comes out below 0.5, the model says this is a no. So 0.5 is the default that's built into every software package I've ever used. 0.5 is the default. It's called the threshold for determining whether something is a yes or a no, or churn, no churn, or go, stay, or pay, or default on a loan, whatever it is. For two outcomes, it's 0.5. So what you can do is change that in most software. And as you change it, that's where you get these points. So every one of these points is a different threshold for determining a positive or not a positive, a 1 or a 0, a yes or a no. You could say positive or negative. Every one of these is a different threshold. The default in prediction is 0.5. You can change that, but it'll plot the ROC curve for you, so you'll see it. If you were just looking at one ROC curve like this and said, I really want to pick the best point to operate, it would be the point closest to the top left. How close can you get to that point right up here? Of course, it'd be this. So this would be your threshold to give you the most accurate model. Okay, it would certainly give you the fewest false positives and the most false, or the best sensitivity and the lowest false positive that you can get combination. You can get much better, reduce the false positive rate to 0, but you're not going to get as good a sensitivity. Or you can get the sensitivity to almost 1, but you're not going to get near the false positive you want, right? You want to lower this and raise this. So you want to be up here. So the ROC curve gives you lots of insights. I should have given you a picture of a bunch of ROC curves, because that's where you really begin to be able to compare models. Oh, that model has a much better ROC curve than the others. And then you want to compute, or the software will compute for you, the AUC, area under the curve, because again, they might all be bad models. Third thing we have is what we call a lift chart. Now, a lift chart is something entirely different. A lift chart represents the improvement that a model provides when compared against a random guess. Somewhat related, although all the accuracy measures, of course, are interrelated in one sense. They all come from the same data, and they all come from the same basic calculations. But this is called a lift chart. How much of an improvement does the model give me when compared against just guessing? If the number is high and you get a lot of lift, that's considered a good model. Okay, well, how do we get the lift chart? Well, we're going to compare the lift. By the way, before I show you that, we're going to compare the lift scores for various portions of the data set. So it's a little different. Instead of comparing the overall thing, you're looking at portions of the data set and figure out which model is best and which percentage of the cases in the data set would benefit from applying the model. It might not be all of them. So let's look at a scenario. I think the easiest way to explain the lift chart is this little scenario that I found that I like a lot. Okay, remember, we always have past data to build these models. So let's say last year we sent out to 200,000 leads. We bought a mailing list and we sent out to 200,000 leads, a brochure, an ad, a solicitation for a donation, whatever, trying to sell something, marketing material. We sent it to 200,000 leads. 1,579 of them actually became customers. So our conversion rate is 0.8%. So that's last year. Now, we've gone out and bought another mailing list. But we're trying to say, you know, it was pretty expensive to mail to all 200,000 people, considering we only got 1,579 takers. Is there a way of predicting which of these new 200,000 are more likely to take the offer and only mailing to a subset of them? Aha, well, maybe, maybe not. So we're going to take last year's cases, because we know how that came out. Either they did or didn't respond. And we're going to build a model based on last year's cases. And we're going to apply that model to this year's potential cases, clients, customers. And we're going to see what we get. And we're going to use a lift chart. Okay, so we build a predictive model. Again, most likely in this case, a classification model. Customer did respond, didn't respond. So yes, no. And of course, we're going to separate into a training set and a test set. So let's say we put 60% of the data into the training set. That's 120,000 of our last year's cases. And we put 80,000 of last year's cases into the test set. And we set that aside. Then the model goes and trains on the training set. Okay? So once it's done, once the model is done, it says I've found the best fit I can, and we've picked the model we want to use, then we say, all right, I'm going to apply this against the test set and see how well you do. Okay? That's called the holdout sample sometimes. So we take the model and apply it to the holdout sample, the 40%. Remember, that's 80,000 cases. And then we rank the 80,000, you know. We give them a number. How likely are you to respond? Okay? Ordered by score and decile. So let me retract something. It probably wasn't a classification model. It's probably an estimation model, because we're giving each one a score, a continuous number. Okay, my fault. So we take those scores and we line them up. If you got the highest score, meaning you're the most likely person to respond to our marketing materials, you get the top score, and so forth. We rank them. Then we put those ranks into deciles, tenths, if you will, 10 chunks. Okay? Top 10% decile 1, next 10% decile 2, and so forth. Okay, and again, remember, these are historical leads. They've already happened. This is last year's data. So after we've ranked them, we can go look and say, this was the model's prediction, and we rank them based on the model's prediction. Then we go look and say, did they really respond or not? How well did the model do in predicting versus how well it really happened? Okay, so here's the table. Remember, we've taken these 80,000, we've ranked them based on their score that comes out of our predictive model. We've then separated that into decile chunks. Nothing magic about deciles. You could do quartiles, you could do other chunks, but deciles. Then we take a peek. Since this is last year data, we say, okay, these 8,000 we thought were the most likely to respond. They got the top scores. How many of them actually did take the offer last year? 252. What percent is 252 of 8,000? 3.1%. What was our average? So 3.1% of these 8,000 actually bought the product. What was our conversion rate last year for the whole chunk? 0.8%. 3.1 divided by 0.8 is what? 4. So that is the lift. We got a lift of 4, which is pretty substantial. Usually get a lift of 1 point something, but we got a lift of 4. We got 4 times as many out of these 8,000 people responding, meaning taking our offer, than we expected. We expected 0.8%. We got 4 times that. Okay. How about the next decile? Well, those 8,000, we look at last year. Again, this is last year's data. 115 of them responded, which is 1.4%. 1.4 divided by 0.8 is 1.8. So there's a lift. And there's a lift. 1.1. It's getting less, obviously, because the scores are going down. They're not as likely to respond. But we look over here and we say, we're getting quite a lift even down here. And so we might stop by saying we're going to take this year's mailing list, which also has 200,000 names. We're going to run them through the model. We're going to get predictions. We're going to put them in deciles. We don't know how many are going to take it because that's this year's data. We haven't mailed yet. But maybe we're only going to mail to the top 24,000 instead of mailing to all 200,000. Maybe we're only going to mail to the top 20%. Okay, 30%. Maybe we're only going to mail to the top 30% because we might get nearly as many yeses mailing to the top 30% as we do mailing to the whole list. And it's going to be a lot cheaper. So again, you'd have to have cost figures. What does it cost to mail? What do you make from someone who buys the product? And we could figure out where to stop going down this lift thing based on last year's data and applying it to this year's data. That's called a lift curve. Very useful. And again, you can see it's a slightly different way of looking at how well the model works. So again, you can plot a lift curve, which looks a lot like an ROC curve, but it's not. It's a proportion of leads and a proportion of sales. So with only about 15% of the leads, we got 40% of the sales. With 20% mailing to the top 20% of the leads, we got 60% of the sales. And again, knowing the cost figures for mailing out and knowing how much you make for someone who buys the product, you might stop here. Instead of mailing out to everybody, why not just mail to the top likeliest ones to respond? Now, I had a student do this, again, in a neural networks course I taught about, it's probably been 10 years ago now. He worked for a small credit union. They had the previous 2 years before he took the course, they had mailed out to all of their customers, all of their mailing lists. It was all of their current customers. They mailed them all an offer for a new Visa card. It cost them $9 per customer to mail them the materials. Okay, the brochure, this and that, the advertising, and so forth. $9 per customer, and they had 30,000 customers. So they spent $270,000 in mailing costs. They got a taker rate, meaning people who said, yeah, I want another Visa card, of about 3%. So out of the 3% that they 30,000 that they mailed out, They only got about 90 takers. Okay. So, they said, wow. So now he's taking this course, and it happened to coincide when they were getting ready to mail out again. And they were going to do the same old thing. It was 2 or 3 years later, they're going to mail out for another offer for a Visa card or something. He managed to effectively persuade them that he could build a better model. He built a model and did the same thing we've done here based on past data, rank ordered everybody, and it looked like to him that he could mail out to the top 30% based on the model and get almost as many takers. So they did. They said, okay, we'll try it. So they only mailed the 30,000, not the 30,000. I mean, he only mailed the 9,000, not the 30,000. Okay, and instead of getting a 3% response rate, they got about a 8% response rate. So they got almost as many people taking the offer by mailing to a much smaller percentage and saving a lot of money in mail-out costs as they did mailing to everyone. Clear case of a very effective product, very effective exercise, and a solid B in the course. No, he got an A. Okay. As always, and I encourage you, there are discussion items sitting there for you to respond to. It helps for me to see what things you like and don't like in the prediction software. I can send and do send usually some of those recommendations. I collate them and send them to the people at Prediction. They like to hear about feedback from the students. Which accuracy charts do you think would be useful? And you can say, well, in my organization, I think we would like to use the ROC curve. I think we'd use the confusion matrix. I think we'd use the lift chart. And then what did you learn from creating your model? Did you learn something about how easy or hard it is to do? What would you like to see improved? Okay. So your basic assignment for week 7 is to continue to explore, continue to try, continue to develop some cursory models, continue to see if you can get the accuracy charts and compare them. See if you can begin to get insights and understanding. Watch the videos if you haven't already. You should now be ready to roll. Try the walkthroughs. See if they work. See if you can build an actual functioning model. Explore. Ask questions. Try features. Build sample models. Start thinking about and looking at some of the potential data sets for week 8 assignment. Now, I will again warn you that week 8 assignment is still a few weeks off. You shouldn't be finishing that up this week because I think it's important that you diverge early in the learning process and try things before you start converging to doing the assignment. I think that's a very important construct in learning. I would also say you want to look very carefully at the potential data sets. We have, as I said, I think last week, 3 sort of categories. We have the data sets that I have in the classroom, which are relatively small compared to what you'd find in the real world, but certainly usable. Some of them are better suited for prediction model, for classification models. Some are better suited for numerical models. Some don't have a target variable, so they'd be well suited for clustering or segmentation models or association models. So you want to be looking at some of those and using those to try a few things. When you start getting serious about building your assignment for week 8, you will note that you have to do at least one model of each type. You have to do at least one unsupervised model and at least one supervised model. And they don't have to be with the same data set because some data sets are not suited for both. Some data sets you could force to do both. So of the data sets you will have to pick from, the ones I have in the classroom would be the simplest to use. There's also the UCI, University of California, Irvine, UCI data sets. If you put UCI data sets into your search engine, they'll come right up. These are much larger data sets, and they've been around for a long time, and they've been used by many, many people to build prediction models because that's what they're designed for, trial and error. And those are certainly a little bit more robust in most cases, not all cases, than what's in the classroom. The third option, of course, is to go out and get a real data set. There are many out there, and I can give you links to real data sets. If I haven't already provided that in the classroom, I'll go check and see. There are many sources, government data, state data, financial data, etc. However, that comes with a giant warning, and that is that real data is much messier. It'll come with missing values. It'll come with skewed values and so forth. So you'll have to spend more time sort of organizing it before you build the models. The upside is that if you use real data and do a good job with it, then obviously the reward should be higher in terms of a potential higher grade. I say potential because you've got to do a good job with it. You can't just say, well, I used a real data set and it was messy and I built a kludged up model. So, you pick what you can handle. I would say don't try to go using real data sets unless you're very comfortable with the software and the approaches and so forth. And then if you find a real data set that's not too unwieldy, that's great. Because in the real world, you're going to have to use real data. Okay, so that's what you're going to do week 7 next week, or week 6 and 7. What I'm going to do week 7 is I'm going to talk about next week while you're still doing this learning process. Certainly be available to answer questions, and I'll certainly cover a few more features and talk a little more about prediction. But I'm also going to give you a lecture and demo on genetic algorithms. As I mentioned earlier, we felt it was important when we designed the program to show you a little bit of an optimization routine that's pretty neat. You don't have to use it in any assignment. You can, but you don't have to. It's from a company called Palisade. It's used in the real world, as are all the models and all the tools and techniques I teach. It's easy to use, it's inexpensive, and it's powerful. So I'll be doing that for edification purposes. Okay, and now we've reached the final slide, as we have each week. Okay, let me see. Here's a question. Good. It says, do you need to prove the data sets we find on our own before trying to model them? I'm not going to approve them because then I'd have to go through and spend a lot of time figuring out if they've got too much messiness in them. And that would be cumbersome for me to do that for a bunch of people. But if you have a specific question, you look at the data set and have a specific question. Now, again, I wouldn't pick something that has millions of rows. 10,000 is a nice number. I would say if you get up to even 100,000, that's reasonable. Millions of rows, pretty big. How many inputs? Well, let's say it's got 40 or 50 or even 100 inputs. That's not too unwieldy. If it has 3,000 inputs, pretty tough. Pretty tough. You're going to find data sets out there that have thousands of inputs, millions of rows. Those are best saved for the Data640 course, where we're using SAS Enterprise Miner, which can handle hundreds of millions of rows and so forth, and does a lot more. Has a lot more ways of cleaning up and finding outliers, errors, missing values, etc. So yeah, that's not much to go on. It's a judgment call. You might want to spend a little time looking at certainly real-world data sets. If you say, oh, this one doesn't look too bad, okay. But if you find some that are enormous in size, I would not try those for this course. Good question, though. Not a very good answer, because I've left it hanging as to what you do. And again, the models and data sets that are in the classroom, the data sets from UCI, aren't bad. They're quite good. But they're just a little bit smaller, and of course they've been used so many times over the years. They're pretty clean in terms of being messy, which is okay. You're learning something that might be new to you. You don't need to be dealing too much with messy data. In the real world, of course, you would have to do that, and you become real data scientists. Okay, as always, the last slide says if you have questions that are burning in your stomach right now, want to ask, fine. If you have questions during the week that you think would be beneficial for all to see the answer to, put them in the Let Me Have Any Questions. If you have something that applies only to you or a concern and you don't want to put it in the classroom, send me an email. If it's an emergency, call me. Okay? All right, interesting session. There's a lot to digest here. I can give you a lot more readings and links to accuracy measures because you don't have a lot in your textbooks beyond what I've given you, but there are many links out there. I tried to provide some in the extra links section of the guidance each week. So if you look in those supplementary links in the guidance, you'll see links to further explanations. If something is still confusing, I'll give you another explanation. Sometimes if you read how it's explained by a different source other than me, or one of the sources I've provided, it makes more sense to you. That's fine. I don't mind providing anyone with additional links or doing additional explanation from my perspective as to what these things do. So it's important, though, that you have a firm grasp of the importance of selecting the right variables and the importance of understanding and using the correct and the proper accuracy measures before you start just jumping in there and building a bunch of models. Those are important measures. If we're going to build a lot of models, we have to be able to evaluate their accuracy. If you're only building one, you say, well, we go with this one. Well, that's not the way we do it anymore. We build multiple models, and then we need ways to to compare their accuracy. Okay, great. Let me go ahead and stop sharing, as I always do first. Then I'm going to make sure I stop the recording.